How can we apply these principles? We're going to go through several examples here where we look to see how we apply these principles and identify which molecules will have the greatest attractive force. If we go and look at these four molecules, we can see that they all have different molar masses, and there is no possibility of hydrogen bonding here. You don't see any nitrogen-hydrogen bonds or oxygen-hydrogen bonds in any of these molecules, nor do we see that any of these are polar. Okay, so the only attractive force that they have are dispersion forces. In order to identify which of these molecules has the greatest dispersion force, all we have to do is look to see what is the molar mass and which one has the largest. Because bromine has the largest molar mass, we know that it has the greatest intermolecular attractive force, which is the van der Waals or the dispersion forces. Okay, what I'd like you to do is pause this lecture. Go ahead and apply the same principle in this problem. Identify which one of these molecules has the greatest intermolecular attractive force. Pause the lecture, and then we'll go over your answer. To do this problem, the first thing that we do is we recognize that none of these molecules have permanent dipoles. They're all nonpolar molecules. And none of these molecules have the potential for hydrogen bonding. Next, we need to identify which one of these has the highest molar mass, the greatest molar mass. If you look on the periodic table, you will see that fluorine has the smallest molar mass, and iodine has the largest molar mass. That means that iodine will have the greatest intermolecular attractive force, the greatest dispersion force. To do this molecule, the first thing that we need to do is analyze the structure of the molecules. The two molecules have very similar molar masses, so their dispersion forces are going to be about the same. However, this molecule is all carbon-hydrogen bonds. Carbon-hydrogen bonds, or molecules with all carbon-hydrogen bonds, tend to be nonpolar molecules. This molecule has a carbon-oxygen bond here. These hydrogens are bound to the carbon only. So there's a carbon-oxygen bond here, and then a carbon-oxygen bond here. Carbon-oxygen bonds tend to be polar. Therefore, the intermolecular attractive forces that we have for these molecules is that this molecule has dispersion forces only, and this has dispersion forces plus a permanent dipole force, or a dipole-dipole force. That makes this molecule having the greater attractive force. Now pause the lecture and go ahead and try to do this problem. To do this problem, again, we look at the structure of the molecules. Although these molecules are not written out, we do have a structure here that we can see that there are oxygens in this molecule. This molecule has no oxygens in it. This molecule, because it has oxygens, is going to be a polar molecule. This molecule is all carbon hydrogens, and so is nonpolar. Because ethylene glycol is polar, we now know that it has a higher attractive force. To do this problem, I'd like you to analyze the structures and think about which one of these molecules would have the greater attractive force. So pause this lecture, try the problem. To do this problem, again, we look at the structure of the molecules. If I look at this molecule, you can see that it's bromine bound to bromine. There's no oxygen, no hydrogens here. And so you might say, well, the only type of intermolecular attractive force we have are dispersion forces. If I compare this molecule to this one, I will see that they have approximately the same molar mass. So their dispersion forces are the same. If I look at this molecule, though, I know that chlorine is more electronegative than iodine, and so there will be a dipole in this molecule. This means that the bromine is a nonpolar molecule, and the iodine monochloride is a polar molecule. As a result of this being a polar molecule, it will have the greater intermolecular attractive force. I'd like you to pause the lecture now and draw a hydrogen bond between the ammonia molecule written below and another ammonia molecule. Use the principles that you learned in how one water molecule will hydrogen bond to another. Remember that it is the positive in one molecule being attracted to the negative in another. So assign your dipoles and think it through.
In order to think through this problem, the first thing that we need to do is put a dipole in on the bonds between the nitrogen and the hydrogen. Then we realize that another molecule that would come up to this would have to have whatever its positive end oriented toward the negative end of this molecule, or its negative end oriented towards the positive. Well, let's start with the nitrogen, and we see that it's del negative. So that means if we bring another ammonia molecule close to it, to the nitrogen, then the positive end of that ammonia molecule would need to be near it. So we can bring up another one just like this, and you can see I have the hydrogen, which is del positive on this molecule, coming close to the del negative on the other molecule. After drawing the ammonia molecule in, then I would put a dotted line for the hydrogen bond. Remember, a hydrogen bond is not a bond, it's an attractive force, so we just use a dotted line. Now, you may not have used the nitrogen on this ammonia, but instead brought another ammonia molecule up to a hydrogen, and that's fine. So let's look at how we would do that. Attracted to the del positive of the hydrogen on this ammonia molecule would be the del negative in the other molecule. So we need to bring another molecule up to this hydrogen-nitrogen end first. And of course, the lone pair has negative charge in it, so it would be trying to get closest to the hydrogen also. So now that we have it oriented correctly so that the del positive on one molecule is close to the del negative on the other, then we draw in our dotted line. So you could have drawn either of these, or you could have had either of the other hydrogens having a hydrogen bond to them. One ammonia molecule actually can participate in 4 different hydrogen bonds.
All right, now we're going to look at these 2 molecules, and we're going to decide which one of these has the strongest intermolecular attractive force. If I look at these 2 molecules, I can see that the hydrogen sulfide has a larger molar mass. But dispersion forces are weak, and the difference in molar mass between water and hydrogen sulfide is rather minimal. So there would be a stronger dispersion force here, but not very large. If I look at this molecule, this would be a very strongly polar molecule, and this would be a slightly polar molecule. The difference in electronegativity between hydrogen and oxygen is very large, and between hydrogen and sulfur is very small. But right now we've just been discussing dispersion forces between these two and permanent dipole or dipole-dipole forces between these. And what the greatest difference is, if we look at this molecule, we see there is a hydrogen-oxygen bond, so it can hydrogen bond. If I look at this molecule, there is a hydrogen-sulfur bond, but not a hydrogen-oxygen bond. Hydrogen-sulfur bonds cannot hydrogen bond. So if I look at these two molecules, this molecule, the water, can hydrogen bond and so has the strongest attractive force. We actually see this in its behavior. At room temperature, water is a liquid and hydrogen sulfide is a gas. Now what I want you to do is to look at these two molecules and decide which one of these compounds has the ability to hydrogen bond, and therefore which one would have the greatest intermolecular attractive force. So pause the lecture, analyze the molecules, and decide. To do this problem, what we do is we have to analyze the structures. The first thing that I notice about these two molecules is they both have about the same molar mass. So they will have about the same dispersion force. Both of these molecules have carbon-nitrogen bonds, so we can recognize that both of these molecules are polar. However, this molecule has a nitrogen-hydrogen bond. That allows it to hydrogen bond. If I look at this molecule, I see there are hydrogens in here, and they are next to this nitrogen, but they are not attached to the nitrogen. Hydrogen may only form one bond, and the way that we write molecules is that hydrogens written after an atom are always attached to that atom. So these hydrogens are attached to this carbon only because they can only have one bond. This nitrogen has no hydrogens attached to it. So which one has the greatest intermolecular attractive force? This molecule can hydrogen bond, this one cannot. So this molecule has the greatest intermolecular attractive force. Now what I'd like you to do is analyze these molecules and answer the question, which one of these has the greatest intermolecular attractive force? When we analyze these molecules, we'll see that this molecule here, ethane, has only nonpolar forces. It's all nonpolar, and so it only has dispersion forces. This molecule right here, of course, has dispersion forces because everything does, but it also has a carbon-hydrogen bond, so it is a polar molecule and has dipole-dipole forces. If we go to methanol here, methanol has a carbon-hydrogen bond, so it has a dipole-dipole force, but it also has an oxygen-hydrogen bond, and so it can hydrogen bond. Because it can hydrogen bond, this molecule here has the greatest intermolecular attractive force. Now we're going to look at the effect that intermolecular attractive forces have on behavior. The only behavior that we're going to examine is melting point and boiling point. There's a number of other characteristics that are determined by intermolecular attractive forces, but we're not going to go into them. Boiling points and melting points are all determined by how tightly molecules will stick to each other. Compounds that have only weak attractive forces, like small London dispersion forces, have low melting points and boiling points. Those that have dipole-dipole interactions will have a larger intermolecular attractive force, and then those that can hydrogen bond have even greater intermolecular attractive forces. Now realize that all molecules have dispersion forces. All molecules that can hydrogen bond also have dipole-dipole interactive forces, but those compounds that can hydrogen bond have greater intermolecular attractive forces because they have all of those forces on top of them. So what we see is those compounds that can hydrogen bond have the greatest boiling points and melting points if their molar masses are all the same. Here's an example. These two molecules have about the same molar mass. Methane has a molar mass of 16. Water has a molar mass of 18. They're essentially very close to each other, so the dispersion forces are about the same. However, water can hydrogen bond, so we see that its boiling point is much higher than that of methane. Also, its melting point is much higher than that of methane. That intermolecular attractive force being very large causes the melting point and boiling point to be very large. If we compare these two molecules, we can see that there's no possibility of any hydrogen bonding because we do not see any oxygen-hydrogen bonds or nitrogen-hydrogen bonds. We also can see both of these molecules are nonpolar, so there's no dipole-dipole forces. The only intermolecular attractive force that these two molecules have are dispersion forces. And of course, the larger molecule will have the larger dispersion force. Butane, therefore, has the greater intermolecular attractive force, and its melting point and boiling point reflect that strong intermolecular attractive force compared to propane. The stronger intermolecular attractive force results in a higher boiling point and a higher melting point, as you can compare butane to propane. We can apply these same principles to these molecules that we've already examined. We've already examined these molecules and seen that they are nonpolar, so no dipole-dipole forces, and they cannot hydrogen bond, so the only intermolecular attractive force that they have are van der Waals or dispersion forces. We compare dispersion forces based on molar mass, and so we know that the molar mass of bromine is greatest, so the intermolecular attractive forces for bromine is largest. The molar mass for nitrogen is the smallest, and so the intermolecular attractive force for nitrogen is the smallest of all of these. This is reflected in their melting point, in that bromine will have the highest melting point and nitrogen will have the lowest. Bromine is a liquid at room temperature, and nitrogen is a gas at room temperature. The boiling point of bromine is also highest, and the boiling point of nitrogen is also lowest. Here's another example. I can compare these two molecules. They have approximately the same molar mass, and so the attractive forces that they have, dispersion forces or van der Waals forces, are about the same. However, this molecule over here, called dimethyl ether has a carbon-oxygen bond here and a carbon-oxygen bond here. This molecule has a permanent dipole in it, so it can have a dipole-dipole force. That makes this molecule have a larger intermolecular attractive force. As a result, the boiling point for dimethyl ether is greater than that of propane over here on the left. Now, what I'd like you to do is to pause the lecture and use the same principles that we've just discussed to use intermolecular attractive forces to determine which one of these molecules would have the highest melting point. Okay, to do this problem, we look at the molecules and you see there's no polarity and no hydrogen bonding possible. They're all nonpolar, so the only intermolecular attractive force is dispersion forces, which are proportional to molar mass. Iodine has the greatest intermolecular attractive force because it has the greatest molar mass. That means that iodine has the greatest melting point. Pause this slide, do the problem, and then resume. In looking at these molecules, you can see that ethylene glycol is carbon-based and also is acetylene. But ethylene glycol has oxygen in it and acetylene does not. This means that ethylene glycol will be polar and acetylene will be nonpolar. Because ethylene glycol is polar, its intermolecular attractive forces will be greater than that of acetylene. As a result, both the boiling point and the melting point for acetylene will be lower. Now pause the lecture and determine which one of these two molecules has the higher boiling point. To determine which one of these molecules will have the higher boiling point, we look at their structures and we think about what intermolecular attractive forces each would have. The only intermolecular attractive force this molecule will have will just be dispersion forces. This molecule will have dispersion forces of approximately the same magnitude as that of bromine because the molar mass is the same. However, iodine monochloride has a dipole in it because you have two different atoms, of which chlorine is the more electronegative. So this is a polar molecule and will exhibit dipole-dipole intermolecular attractive forces. Because iodine monochloride will have dipole-dipole forces, it will have the larger intermolecular attractive force. This means it will have the higher boiling point. Now examine these molecules and determine which one of these has the higher melting point. And in examining the structures of these molecules, we can see that propylamine, this one on the left, has the ability to hydrogen bond, whereas trimethylamine, the one on the right, cannot hydrogen bond because there is no hydrogen attached to the nitrogen. This means that the intermolecular attractive forces for propylamine is higher, and that gives it the higher melting point, and it would give it the higher boiling point also. Pause the lecture and go ahead and determine which one of these would have the greatest boiling point. In analyzing these structures, you can see that ethane right here is a nonpolar molecule and it cannot hydrogen bond. This molecule will only have dispersion forces. If I look at methanol, I can see that it can hydrogen bond. It has a carbon-oxygen bond, so it's polar. And of course it will have dispersion forces. The size of this dispersion force will be about the same as that as ethane because the molar mass of methanol is about the same as that of ethane. If I look at this molecule, I can see that it's a polar molecule because it has a carbon-oxygen bond, and of course it will have dispersion forces that will be on the same order as the other two molecules. But it cannot hydrogen bond because there is no hydrogen attached to oxygen. This means that the molecule with the highest intermolecular attractive force will be methanol due to its ability to hydrogen bond, as well as having the other intermolecular attractive forces in it. The one with the lowest intermolecular attractive force will be ethane, since it can only have dispersion forces. Because methanol has the highest intermolecular attractive force, it has the highest boiling point and would have the highest melting point as well. Because ethane has the lowest intermolecular attractive forces, it has the lowest boiling point and would have the lowest melting point also.